The light touching your face right now is older than the sun. And depending on how you measure it, some of it might be older than the universe itself. That sentence should bother you. If it does not bother you, you have not understood it yet. Let me start with something everybody knows. The sun is about 93 million miles away from us, and light moves at roughly 186,000 miles per second. So it takes sunlight about 8 minutes to get here. Simple enough. That means when you look at the sun, you are looking 8 minutes into the past. Fine. Nothing strange there. But what if I told you that those photons, the actual particles of light that left the sun's surface 8 minutes ago, were not created 8 minutes ago? They were not created 8 years ago. They were not created 800 years ago. The energy in that sunlight was born somewhere between 10,000 and a couple 100,000 years ago, deep inside the sun's core. When woolly mammoths still walked the earth, when glaciers covered half of North America. That particular packet of energy is ancient, and it only just now reached your skin. How is that possible? How can something moving at the fastest speed in the universe take 100,000 years to travel a distance a straight-line photon covers in 2 seconds? Here is your first clue. The core of the sun is extraordinarily dense. We are talking about matter compressed so tightly that a photon, a particle of light, can barely travel a few millimeters before it slams into an atom, gets absorbed, gets re-emitted, in a completely random direction. It might head outward, it might head sideways, it might head straight back toward the center. There is no preference. This process has a name. Physicists call it a random walk. You can picture it like this. Imagine a man stumbles out of a bar at midnight and tries to walk home, but every few steps, he spins around and staggers off in some new random direction. He might take 1,000 steps and end up only 30 feet from where he started. He is moving constantly, but getting almost nowhere. That is what a photon does inside the sun. It bounces, trillions upon trillions of times, absorbed and re-emitted, each time sent tumbling in some new arbitrary direction. The sun is only about 700,000 kilometers from its core to its surface. A straight shot at the speed of light takes about 2.5 seconds. 2.5 seconds, remember that number. But because of this random stumbling, the energy that starts in the core takes tens of thousands of years, some estimates say over 100,000 years, to drunkenly wander its way to the surface. The fastest thing in the universe, delayed by a factor of more than 1 billion, not because anything slowed it down, it was always moving at the speed of light between each collision, but the path itself is so tangled, so absurdly convoluted, that the net progress outward is almost nil, and there is an important subtlety here. The photon that finally escapes is not the same photon that was created in the fusion reaction. It has been absorbed and re-emitted so many times that it is more like a relay race of energy. The original gamma ray from the fusion event gets chopped up, scattered, degraded, until what finally breaks free from the surface is visible light. Millions of individual photons, each carrying a tiny fraction of that original energy. The identity of the photon does not survive the journey, but the energy does, and the energy is old. So already the sunlight on your face carries energy that predates human civilization. But that is not what I really want to talk about. Let me take you somewhere stranger. If we look past the sun, past the stars, past the galaxies, past everything, we eventually hit a wall. Not a wall of matter, a wall of light. It is the oldest light in the universe. We call it the cosmic microwave background. And it is everywhere. Every direction you point a radio telescope, there it is. A faint glow, almost perfectly uniform, filling the entire sky. This light was released about 380,000 years after the Big Bang. But before that moment, the universe was so hot and so dense that photons could not travel freely. They kept crashing into electrons and protons, getting scattered, getting trapped, like trying to see through a fog so thick you cannot see your hand in front of your face. Except this fog was not made of water. It was made of loose particles, a screaming hot plasma filling all of space, and every photon was pinballing through it with no hope of escape. Sound familiar? The same random walk, the same drunken stumble, except this time it was not just one star. It was the entire universe acting as a prison for light. But as the universe expanded and cooled, the temperature dropped enough for electrons and protons to finally combine into hydrogen atoms. The fog cleared, and all those trapped photons were suddenly free to fly. That moment is called the surface of last scattering. It is the oldest snapshot of the universe we can ever see. And those photons have been traveling ever since, for about 13.8 billion years, getting stretched by the expansion of space until they cooled from a searing 3,000 degrees down to just a few degrees above absolute zero. Microwaves now, invisible, but still there, still flying. So here you have light that has been traveling for nearly the entire age of the universe. 13.8 billion years of flight. That sounds like the oldest thing there could possibly be. Nothing in the universe is older than the universe, right? Well, that depends on what you mean by old. And that is where things get genuinely weird. See, here is the trouble. We have this beautiful theory called special relativity. Einstein's theory. It tells us that time is not the same for everyone. If you move fast, your clock runs slower compared to someone standing still. The faster you go, the slower your clock ticks. And as you approach the speed of light, your clock approaches a stop. Not because anything is wrong with the clock is fine. Time itself slows down. Now, photons do not approach the speed of light. They are at the speed of light, always from the instant they are created to the instant they are absorbed. So what does that mean for a photon's experience of time? If you naively plug the speed of light into Einstein's time dilation formula, you get a division by zero. The math breaks. It does not give you zero time, it gives you nonsense. And this is not a minor technical glitch, it is telling you something fundamental. A photon does not have a valid frame of reference. There is no perspective, no point of view that rides along with a beam of light. It is not that time goes to zero for a photon. It is that the entire concept of time, duration, before and after, simply does not apply to light the way it applies to you and me. Let me say that again, because people get this wrong all the time. It is not that a photon experiences zero time. It is that asking how much time a photon experiences is like asking what north of the North Pole is. The question does not have an answer because the question does not make sense. So here is the detective problem. We said the cosmic microwave background has been traveling for 13.8 billion years, measured by our clocks, our time, our reference frame. By every standard we have, those photons are almost as old as the universe. But those same photons exist on what physicists call a null world line, a path through space-time where the interval between departure and arrival is zero. Not approximately zero, exactly zero. From the geometry of space-time itself, the creation and absorption of a photon are, in a precise mathematical sense, zero distance apart. Not just in space-time. So is that photon 13.8 billion years old? Or is it 0 seconds old? Or is it meaningless to even assign it an age? You might think this is just philosophy, just wordplay. It is not. It matters, because it tells us something disturbing about what time actually is. We have this deeply ingrained notion that there is a universal clock somewhere, that time flows like a river, and everything in the universe rides along together. That notion is dead. It has been dead since 1905. But most people have not attended the funeral yet. Time is local. Time is personal. Your clock and my clock do not have to agree. And a photon does not have a clock at all. Now I want to show you why this is not just a cute theoretical point. Something happened recently that made this question urgent, practical even. In the last few years, there is a telescope called the James Webb Space Telescope. It was launched in the early 1980s. No, wait, let me be careful here. It was a project that was in development for decades, and it has been looking at the very early universe with infrared eyes sharper than anything we have ever had, and it found something troubling. It found galaxies that should not exist. These galaxies appeared in the images from the earliest periods of the universe, just a few 100 million years after the Big Bang. And they were big, massive, mature-looking. Galaxies are not supposed to look like that when the universe was so young. Our best models say it takes billions of years for enough gas to collect, enough stars to ignite, enough mergers to happen, for galaxies to grow to the size we were seeing. But there they were, huge galaxies apparently existing before they had any right to. Some people started saying cosmology was broken, that the age of the universe must be wrong, that maybe the universe is not 13.8 billion years old. Maybe it is much older, maybe 26, 27 billion years old. And if that is true, well, everything shifts. All our calibrations, all our measurements. The light we thought we understood becomes a different story entirely. Now, I should be careful here because the scientific community is still working through this. Several research teams have shown that some of those early galaxies are not as massive as they first appeared. Some of them have black holes at their centers that make them glow brighter than you would expect for their actual size. Others may have experienced bursts of star formation, brief episodes where they made stars at an extraordinary rate, appearing temporarily brighter and bigger than they really were. So it is possible, maybe even likely, that our standard model of cosmology survives this challenge. But the fact that the challenge was taken seriously at all tells you something. It tells you we are not as confident about the age of the universe as we sometimes pretend to be. And there is another crack in the foundation. Physicists have been arguing for years about something called the Hubble tension. We have two ways of measuring how fast the universe is expanding. One method looks at the cosmic microwave background, that ancient light, and works backward using the known physics of the early universe to figure out the expansion rate. The other method looks at nearby stars and galaxies, measures their distances carefully using a chain of different stellar objects, each one a little farther out, like stepping stones across a river, and calculates the expansion rate from their motion directly. These two methods should give the same answer. They do not. They disagree by a significant amount, persistently, stubbornly, and nobody can fully explain why. It is not a small discrepancy you can wave away. It is the kind of disagreement that suggests either one of our measurements is wrong, or more excitingly, there is something about the universe we do not yet understand. If the expansion rate is different from what we thought, then the age of the universe is different from what we thought. And if the age is different, then the age of every photon that has been traveling since the universe began is different too. But also, as we just established, the age of a photon is not really a coherent concept in the first place. Do you see what has happened? We have been chasing this question, is light older than the universe? And the deeper we dig, the more the question itself falls apart. It is like pulling a thread on a sweater and watching the whole thing unravel. Here is what I think we can honestly say. Time is not what you think it is. It is not a river. It is not a stage. It is not a backdrop against which things happen. Time is woven into the fabric of space-time, and how you experience it depends entirely on how you move through that fabric. Anything with mass drags through space-time and accumulates what we call age. Light does not. Light rides along the seams of space-time on null paths where the distinction between past and future collapses into a geometric point. When someone says, this photon is 13 billion years old, they mean something precise but limited. They mean, in our reference frame using our clocks, 13 billion years have elapsed since that photon was emitted. That is a true statement, but it is not the only true statement. You could equally well say that from the geometry of the photon's own worldline, no time has passed at all. Also true. These are not contradictions. They are different descriptions of the same reality, from different vantage points. Nature does not owe us a single consistent answer to the question, how old is this thing? Nature gives us a space-time. If we want an age, we have to specify whose clock we are using. And for a photon, there is no clock to use. I find this beautiful, genuinely beautiful, because it means time is not some absolute tyrant that everything must obey. It is more like a local weather pattern. In your neighborhood, it rains. In the photon's neighborhood, there is no weather at all. And there is one more thing that I think people miss about this whole business. We keep talking about the age of the universe as if it is a single number, 13.8 billion years, stamped on the box. But even that is a choice. That number is the age measured by a very specific type of clock, a clock that has been sitting still, more or less, relative to the average motion of all the matter in the universe since the Big Bang. A co-moving clock, they call it. If your clock had been moving differently, you would get a different number. The age of the universe is not written into the universe. It is a measurement that depends on who is doing the measuring. So, can light be older than the universe? In one sense, absolutely. The energy in a photon from the cosmic microwave background has existed since the universe was less than 400,000 years old. That energy has been around for almost the entire history of the cosmos. In another sense, light has no age at all because it exists outside the framework where age means anything. And in a third sense, we may not even be sure how old the universe is in the first place because the measurements do not all agree, and telescopes keep showing us things that make us second-guess our arithmetic. The real lesson here is not that light is old. The real lesson is that time is stranger than you have been told. It bends, it warps, it vanishes, and the thing that moves fastest through our universe does not participate in it at all. Think about that tonight. When you look up at the stars, every single photon landing on your retina has taken a journey where, from its own geometric perspective, departure and arrival are the same event. The star in your eye, the Big Bang in your face, separated by billions of years on your clock, separated by nothing at all on the photon's world line. Both statements are true, and neither one is more real than the other. That is what I want you to sit with. If it does not keep you up at night, maybe think about it a little harder,